so the last time we talked about Cartan's criteria, right? So today start talking more about semisimple Lie algebras. Right. So what do I want first? So, okay. So first thing is that I promised that semisimple is actually direct sum of simples. Our definition was different, so first let us fix this. For that, we need the following proposition. Which says that if I have semisimple Lie algebra and I have an ideal inside, then there exists an orthogonal complement, which is not only orthogonal complement in vector space sense, but also it's an ideal. Okay, so then there exists an ideal I prime in G such that G is I plus I prime.
Plus with respect to the killing form.
Plus with respect to just vector space structure there.
Okay.
I mean,
Well,
which is
what do we mean by orthogonal? Is it
orthogonal with respect to it's complement in the sense that this direct sum is in vector space sense, but also in Lie algebra sense, since I said that it is an ideal. Yeah.
okay?
So it means that every element from here is a sum of elements from here and here, and also they do not intersect, I and I prime. So that's what it means. All right, so we actually, but you're right. Here orthogonal also means orthogonal with respect to killing form as well. It's just because killing form gives us good instrument for working with semisimple Lie algebras. So proof. So let me take I to be I prime to be orthogonal complement, right? This is with respect to the killing form. Then we know that I prime is an ideal, that we proved, right? Because of an invariance of the form. So how to prove this? So I would like to prove that I want to see that I intersect I prime is just empty. So they do not intersect. Right. So
Shouldn't we intersect by 0?
well, yeah, by 0. Sorry. Yeah, empty in vector space sense. Right. Okay, so I claim that I intersect I prime is also an ideal That's clear, right? But it's also, I claim that it is a solvable ideal. Why? Because what is the killing form here? It's just a restriction of killing form, right, on G to this ideal, right? But then by definition, this is an orthogonal complement to this one, right? So therefore, if I take killing form of X and Y, where both these things live in here, right? So X is orthogonal to Y and the other way around. So therefore, this is 0, right? But by Cartan criteria for solvability, this means that this ideal is solvable, right? So criteria was that K, G, G, G equals 0, G is solvable. Let me take a parenthesis. Okay, so this is a solvable ideal in G, and G is semisimple, right? So it is 0. So therefore, sum of these two is a direct sum. On the other hand, the sum spans everything because the killing form is non-degenerate, right? So let me put it like that. So that I plus I prime is the whole G because killing form is non-degenerate. So for example, we can organize Gram-Schmidt process, right? Take a basis in I, right? And complement it to I prime, and then Gram-Schmidt it with respect to a killing form, right? Then you will get, I mean, you take a basis in I, right? And complement to the basis of the whole G. Right, and then Gram-Schmidt it, right? So you'll have orthogonal with respect to killing form in I, right? And all other vectors will be orthogonal to everything in I, right? Because you orthogonalize it. And so therefore, they all will live in I prime. So therefore, I and I prime span the whole G. So this is just basic linear algebra. And so therefore we have, but since they do not intersect, G is just I direct sum I prime.
Why K is not generate? We have this. Can you explain it again?
Which particular?
Because K is non-degenerate. How
How we can know this? Okay, so I claim that the following. So let me take the following basis of G: V1, V n, where the first K is a basis of I. All right, this I can do. Then I start doing Gram-Schmidt process with respect to K. This I can do because K is non-degenerate. And I divide by a norm of vector this process, so everything works. So what do? I take V1. So first I orthogonalize these vectors inside I, right? And then I start with Vk plus 1. Make it orthogonal to all of this. Then Vk, all others will belong to I prime, right? So this is a basis. After Gram-Schmidt this, right, this will be a basis in I, and because this is orthogonal, this will belong to I prime, and this will be a basis of I prime. So together they span actually G, because this is, originally this was a basis in G. For example, this, there are different ways how you can deduce it from linear algebra. You can also say that since it's non-degenerate, then so all elements in I prime, they are described by, so you have corresponding number of equations defining orthogonality for you as well, right? And these equations, they never degenerate because the form is not degenerate. So that's another explanation. But for me, I think it's this one kind of works better. Okay, and we will have corollary of this. Is that G is semisimple. It's the same thing as G is a direct sum of simple Lie algebras. So direct sum like this, where G, all these ideals inside which are Lie subalgebras as well, are simple. All right, so let us prove this. Okay, so let's prove it this way first. So proof. Okay, this way. It means that suppose that I have decomposition like this, and then I want to see that G is semisimple, and of course we would like to do it in standard way to prove that the killing form is non-degenerate. Okay. So killing form restricted to each G1, G2, Gk is non-degenerate, right? Because it gives killing form on each of these simple Lie algebras. Okay. So we will use this. Okay, so fix some x in G, right? Any x. Then we'll have decomposition. Since we have this decomposition for each element, I can write it like this: x1 plus x2 plus so on plus x k, where xi belongs to gi. All right, we can what we would like to see that there exists some y in G such that the killing form of x and y is non-zero. Then we are done, right? So we chose, so for any element, there exists some other element such that this form is non-zero. So there are no non-degenerate elements. Okay, so that's our goal. So of course, this element that we would like to choose here is non-zero, right? Killing form 0 with anything else is 0. So we don't. So if it's not 0, and the decomposition, this is indirect sum, we can at least one of these xi's is not 0, right? So without loss of generality, assume that it's x1. Okay. Then we know that there exists y1, right, in G1, such that k G of x1 and y1 is the same as kg. This is the same as k G1 of x1 y1, right? Because both x1 and y1 are in G1, right? And the killing form on G1 is just a restriction of killing form on G. Okay, so but we can choose y1 since this form is non-degenerate, right? G1 is simple. We can choose y1 such that this is not 0. Very well. Then I claim that kg of x with y1 is not 0. So it is claimed, so let me explain it now. So x is the original x, and I claim that y1 is the other element that, like this. Yeah, is the other element that I need to make this form a non-zero for x. So this is because, a claim follows from the following observation. K of xi and y1 is 0 for every I not equal to 1. This is just because they live in different orthogonal components. All right? So let me again draw a picture with blocks, right? So killing form, again, we should remember what is this killing form. It's a trace, right? Add xi at y1. Right? So I claim that first of all, we have the following two observations, that at xi of g j is 0, right, for I not equal to j, right? This is just because this is direct sum in Lie algebra sense, right? If I take an element from here and from here commute, this will be 0. So that's exactly what is written here, right? Because xi, so I'm taking commutator of xi with something from another component, right? On the other hand, add xi of gi is inside gi, just because it's a subalgebra, right? So from these two facts, I can draw a picture of add x I in some basis, right? Well, there exists a basis. So this is just like that. You have a block, so it's block diagonal first of all, right? And somewhere you will have a block which is add xi, but in smaller algebra gi. and everywhere else are zeros. And actually here as well. So just these two facts says that if I choose basis, like the first vectors are basis in G1, these are then next elements of basis is a basis in G2 and so on. So in this basis, the matrix looks like this. And for the same, exactly the same reason, at y1 is then, so now I have something in the first block, right? Add y1 in G1. And then zeros everywhere else. For the same exact reason. Very well. So therefore we have this, right? So I have two matrices of this sort, right? And blocks. In y1 you have block in the first place. In add xi you have for I greater or equal than 2, you have block somewhere else. So product is 0, trace of 0 is 0. Okay. So we have this, but why from this we have the claim? Yeah, the form is bilinear, right? So k of x and y1 is k of x1 y1 plus k of x2 y1 plus and so on, right? Because x is like this. So all these terms are zeros because of this. And this is not 0. So this is not 0, but there's nothing else to cancel it, right? So this is 0. This is not 0. That's it. So we proved this direction, right? So we have decomposition. Therefore, it's semi-simple. So let's prove the other direction. So we suppose that G is semi-simple, right? So that's why it is corollary of the previous proposition because of this direction. Okay, so now I start kind of decomposing, right? So suppose I have non-zero proper ideal in G. Right, then G can be written as I1 plus I2, where I2 is also a non-zero proper ideal. Right, this is because of the proposition that we proved in the beginning of the lecture. All right, so this is by proposition. But also, if I found such I1 and I2, I claim that they are semi-simple. So again, claim I1 and I2 are semi-simple. Why is that? Say what?
G mod y1 is G mod I1 is I2.
Right. We never proved the quotient of semi-simple. Actually, yes, this is true, but this follows from what I actually proving. Yes. But again, we would like to use a killing form. So we have killing form on G. It's non-degenerate, right? Suppose that the restriction is degenerate, right? So suppose, proof of claim. So suppose that ki 1 is degenerate. So what does it mean? It means that it means that there exists some x in I1, right, such that k I1 of x and y is 0 for all y in I1. Right? But let me take some z, just any z from G, right? Then, because I have this decomposition, I can write it as z1 plus z2, right? This lives in I1, this lives in I2. Then let me consider killing form on G, take this x that I found, and plug z. And z is any. This is important. Then I will have what? K g x with z1 plus k g x with z2. So this is 0 because x is like that. Right? Because this is this is an element in I1, this is an element I1, and ki1 is a restriction of kg to I1, right? So therefore, this is the same as ki1 of x and z1. So therefore, this is 0 because this is 0 for any y in I1. So I claim that this is 0 as well. Just because of this, right? They are in different orthogonal components, and so we can just draw the same picture with blocks, right? Yes. So let me maybe indicate it like so, because the sum I equals I1 plus I2 is, G equals I1 plus I2 is direct. So therefore, if my we are proving that I1 is semisimple by contradiction. Suppose it's not semisimple, then the form is degenerate. Then we have a contradiction because killing form on G is degenerate. So contradiction, therefore, I1 is semisimple, and by the same reasons, I2 is semisimple. So contradiction. Maybe I should use this sign here, so for any. So therefore, I1 is semisimple, and similarly, I2 is semisimple. Very well. Then, so now if I take G found a non-zero proper ideal inside, then I decomposed it, then I have a direct sum of two semisimple Lie algebras. And then I repeat it, right? So since they're semisimple, I can apply the same process to I1 and I2, right? So similarly, if I1 has non-zero proper ideal, say I11, so then I1 is I11 plus I12, where these are ideals in I1, and they are both semisimple again. And for I2, we also can do this. And then for I11 also. So we do this again and again. Each time they are proper, so I reduce, on each step I reduce dimension. But since G is finite dimensional, at some point my ideal will have no non-zero proper ideals, right? So it means that this ideal is simple Lie algebra by definition. Right. Again, yes. So this process is finite because dimension of G is finite. So therefore, G is G1 plus G2 plus some Gk, where Gi's are simple. Okay. So this is important. So usually people think of semisimple as direct sum of simples, maybe, but for theoretical reasons, it's important to introduce them like we introduced. But then this falls. Okay, so now you can deduce a bunch of stuff out of that. So let me formulate something. So proposition so let G again be semisimple. And we have therefore decomposition into simples. So then so how to formulate it better? Yes. Any ideal of G, any ideal I of G is of the form I is a direct sum of some of Gi's. I from some set J, right, of gi's, and J is a subset of numbers from 1 to k. Subset of a set of numbers from 1 to k. Right, and from this it immediately follows that right. So let me think how to put this better. So let me just enumerate statements. So first is this one. Second is that any ideal of simple, semi-simple Lie algebra is semi-simple, and not only ideal but also quotient as well, or quotient. Let me add here. And number 3, which is also an easy statement, if G is semi-simple, then the commutant of G coincides with G. For simple, it's like just immediate. For semi-simple, you need to use this decomposition. And it's almost obvious. You still have to say something. So proof of this, let me make it exercise. So it's a good exercise to understand the proposition that we proved in the beginning. And so will be, so exercise will be in the problems for seminars, for a seminar. It will not give us any insight of how things proved, but rather I will let you practice. But we will use this, for example, a lot, so that quotient or an idea of semi-simple is semi-simple. Very nice. So this is one thing that I wanted to say. Another thing for today, let us introduce the Casimir operator. So this operator is important for the structure theory of Lie algebras and for representation theory, of course, but it's also important in math physics because it's closely related to the spherical part of Laplace-Beltrami operator on some symmetric spaces. So when you consider some and thus with some Hamiltonian systems, for example. Anyways, you will see it. So it's important for various reasons to introduce it. Anyway, I think last semester we saw the Casimir operator for SL2, right? Nothing for SLN. Maybe we did something in problems. I don't know. I don't remember. So okay. Anyways, all right. So proposition. We start with the proposition. So let be non-degenerate invariant by linear form on semisimple Lie algebra. Actually, on any Lie algebra. That for semisimple we know that we have one, right? On some Lie algebra G. And let x1 so fix some basis. So let x1, xn be basis in G. And let us denote a dual basis to this one with respect to this form with upper indices, as physicists like. So let x1, xn be the dual basis. So this is dual basis with respect to our form. So therefore, it is a basis still in G. Okay. Dual means that B of xi, xj is delta ij, right? I can do this because the form is non-degenerate. So these are all the conditions. Then the element
It probably doesn't matter in this context, but shouldn't you write delta with one lower and one index?
I don't know. You tell me if this is just Kronecker delta. It doesn't. I'm not considering any transformation rules of it, right? So I guess this doesn't matter too much. Yeah. Yeah. So it means that it's 1 when they coincide and and 0 when they don't. Okay. So the element, which one? So let me introduce it. Let's call it CB. And so it is like that, xi, x upper index I from 1 to n. And so this is an element of what? Of a universal enveloping, right? It lives in U of G. Does not depend on the basis that we chose. And it is actually belongs to the center of universal enveloping. So it's central and it's actually something canonical, kind of. Let's prove this. All right, so let me consider an isomorphism between G and linear functionals on G. So between G and G star. Let me call it, so proof let me call it psi, corresponding to the form B. This is a natural isomorphism from G to G star, right? I'm taking an element X, right, and put into correspondence to X linear functional like this. Okay. So I claim that psi b, psi b is an isomorphism of vector spaces, of course, because B is non-degenerate. But also it is an isomorphism of representations of G. So G is, so this is a joint representation. This is a coadjoint. So let's check it. Right? So this follows from invariance. So it's, right.
By Shor's lemma, it's just down.
By Shor's lemma, but Shor's lemmas is for irreducible representations. I never say that it is simple, right? That G is simple. Yes. Some other questions? Okay, so let us check it, right? So let me take some element X and act by another element of G, Y on it, and take psi B. Right? I would like to see that it is Y. It's Y acted on psi B, evaluated at element X. Right? So kind of action and taking psi B commute with each other. So by definition, what it is? Okay. So let me maybe write this. This is like this. Doesn't. So usually we work with symmetric form, so it doesn't really matter. Maybe I just should add symmetric there. So by definition, right? This is the following. It's B, right? So I would like to, yes, I would like to evaluate it at some Z, right? So
Why X on X is just another joint method?
Yes, that's true. That's what I'm going to write here. But each X, Y, and Z are elements of G, right? So I take X, act by Y by a joint representation, obtained another element of G, which is commutator of 2. Then applied psi B, get some functional from G star, and applied this functional to Z, which is another element of G. So this is so instead of this dot, I should put Z. Then instead of X, I should have this action of Y on X. So this is this, right? So this is invariant, therefore I can rewrite it like this, Z, Y, X. So this is negative. So this is B, right, of minus Y acting on X, right? On minus Y acting on Z, sorry. Right? and then x. Right, but then this is psi of x, right, evaluated at minus y applied to z. But this is by definition how y acts on psi as a functional, right? So this is actually y applied to psi b. So this is a co-adjoint action that we have here. And then apply it to an element in x. Then I will have so this is again in G star, right? No, sorry, should be like that. So this is an element in G star. I apply y, get another element of G star, and evaluate it at z. So I started here, ended here. So y commutes with psi. That's exactly what is there. Very, very well. So let me consider now the following element in G tensor G, element like this. So this is for I from 1 to n, this is in G tensor G. So G tensor G is isomorphic to G tensor G star by ID tensor psi b. All right. But so I actually claim then that under this isomorphism, I is going to be just an identity.
I'm sorry, why? It is about this again, but why do we have on the top like a product of a tensor product of an element of the basis and the element of the dual basis?
Yes.
And claim that it lies inside the tensor product of.
Yeah. So this is an element in G. So which element? Like this. I take
so
xi.
It's not the form itself, but the crystal.
Yes, it is dual with respect to this form.
But why? How is it different from xi with lowering stem?
It's just different element. For example, if you take killing form on SL2, right? Then your
Don't we define the dual element as like the dual basis as the one which satisfies like EI with the top index on EI?
so this is the definition. So that's the definition. That's it.
But
it's not definition from the linear space. It's different. They are in the same space, not in a different space.
Yes. Okay. So this is definition. To take a linear form, it eats two elements of G, right? So therefore, I cannot plug in here something from G star. Okay. So I claim that this is exactly an identity operator on G. Right? So so this is the same as in linear transformations on G. Right? And under this identification, my element I is the same as just identity element. You just can directly check it. All right. So next thing. So you see, this already gives us that I do not depend on basis, right? So I is a preimage of just identity on identity transformation on G, right? Under some isomorphism. That's it, right? So therefore, I does not depend on basis. On the other hand, so let me take, so in here, so this space has some natural structure of a representation of G. Has structure of G module. What is the structure? So if I take L from here, some linear transformation, then X acting on L is just by definition X like this. So I have add X, which is also an element in here, right? And I can commute add X with L. So that's the definition of the action. Okay, so I take a transformation from here, element X from here, and then action of X on L gives me another transformation, which is this, right? So this is a commutator. Just I apply L, then add X first, minus add X times L. Right. So another exercise, which I don't want to spend time on the lecture, on this exercise, is that, well, first of all, so another problem for seminar. Check that this is indeed an action. So this is star. Star is indeed an action. And on the other hand, check that this action coincides with one given by this identification, by identification, let's call it somehow double star. Right, so of course, this is a representation of G, this is a representation of G, and tensor product is a representation of G. So therefore, there's some structure of G model here coming from this identification, and another one that I just explicitly gave it to you like this. So there's some check. It's almost clear, right? Because when you act on this, it's like Leibniz rule, right? Acting on this component is actually multiplying from the right, but also you have minus sign because of star. And here is multiplying from the left. So that's how you get a commutator. But you have to write something. Very well. So we have an action like this. We have an element I, which is actually almost an identity, right, up to some isomorphisms. And so what I would like to do now is that, right, so I have a multiplication, right, from G tensor G to U of G, right? So I have, it's just like this. I take a pair, A, B, from here, and just multiply A and B and get an element in U of G, right? So this is just by definition right. So U of G is also a representation of G, right? So how what is the you act on so there's G is the first as a degree 1 component here, right? You act on it by a joint action, but then on the whole U of G you just act by using Leibniz rule, right? So we discussed this action in the first semester, right? But with respect to this action, so M is actually is a homomorphism of representations. Of G. So therefore, I have ID here, which lives in here, well, in here, and therefore in here, right? Then let me make this a chain of isomorphisms. So I have ID on G inside endomorphisms of G. And of course, any x acting on this element is 0, right? So now let me take inverse image of identity, which is I, right? So therefore, x acting on I is 0 as well, right? Because this is an isomorphism of representations as well, right? And this is a representation also, right? So I have some element in here such that x acting on this is 0, right? So maybe let me be more detailed. So therefore, x acting on I, right? So I, remember, is this element. Is x acting on ID tensor psi b of identity on G, right? So since this is representation, isomorphism of representations, I can pull x through and see that x ID tensor psi, this is ID tensor psi b, x acting on IDG, but this is 0. Therefore, the whole thing is 0. On the other hand, we have multiplication there. But m applied to I is exactly CB. So let us take x applied to CB. It is x applied to m of I, right? So again, m is a homomorphism of representation. So therefore, I can pull x through. So it will be m x acting on I. So this is 0. So therefore, the whole thing is 0. So x acting on element of u of g by 0. But again, what is this action? It's actually taking a commutator. So therefore, we proved that so CB commutes with x. X is any, so CB is actually central. So Cx, it's the same as x commutes with CB. But we proved that this is just 0. So therefore, CB is from the center. All right. So why do we need, in the context of our course, why do we need the Casimir operator? To see at least in some case the proof of complete reducibility of finite dimensional representations of all semisimple Lie algebras. It's a very strong result, can be proved in several ways. There's some algebraic proof, which is using Casimir operator. There's Lie group, is using the Lie groups, and what's called whale trick, so compact Lie groups. There's another way to do this. And also some algebraic proofs, they are different. They can be formulated in different words. Anyways, so the next thing that I would like to discuss is complete reducibility of representations of semisimple Lie algebras. So theorem any finite dimensional representation of semisimple Lie algebras is completely reducible. Okay, who remembers what does it mean for a representation to be completely reducible?
This any representation can be decomposed with the direct sum of irreducible functions.
Yes, so if I have an invariant subspace, it has a complement in vector space sense, which is also invariant subspace, right? In other words, so that is any exact sequence. So let me put it like this: for any exact sequence zero v w u 0 we have of representations of G. We have W is a direct sum of V plus U. Direct sum of representations. So what this sequence mean is actually that V is a sub-representation of W, right? So this is all these arrows, they are morphisms of representations, and this 0 here means that this is injective. So this is sub-representation, and quotient of W with respect to V is U. So this map is surjective. I think I should write it like this, I guess. All right. So we will prove this theorem for one particular case. So we will prove the theorem for the case V is irreducible and non-trivial. And U is trivial. So using the Casimir operator. So this case is crucial in the sense that everything else can be deduced from this case. Also, from the case that V is trivial, also it goes kind of separately, but we will not touch it. But this is like a cornerstone of proving this theorem. After that, everything can be pulled out using homological algebra, like cohomology of Lie algebras. It can be all swell out without using homology. It's just a lot of like abstract reasoning thing, right? But the Lie theory structure, Lie algebra theory part is this one, right? So that's why we will see this one, and then for this course I will just say that everything else can be proved using homologies of Lie algebras. I can say more after lecture if you wish, but anyways. So, but before that, maybe. So, how much time do we have? 12 minutes. Ah, okay. So, maybe not. So let's just prove this, and we'll be done. Very good. So then, so the most, it's not hard, but still. So this case follows from the following lemma. So let rho VV be a non-trivial, irreducible representation of semisimple G. Then there exists an element, let's call it CV, in the center of universal enveloping, such that it acts, so rho V of CV, it's actually some constant, right? It acts as a scalar operator in V, because V is reducible and this is from the center, okay? So this is not a statement of the lemma, this we know from before, but we can recall it if you wish. But what's important is that lambda is not 0. So it acts by non-zero scalar in V. And rho C, right, in trivial representation, it acts by 0. So this is the statement of lemma. Proof is the following. So you actually take, suppose that you have so take this form BV that we introduced before. Right, it's a trace form, right? BV of x, y. It's invariant, right? So it's trace over V of rho Vx, rho Vy. Okay. So if it's if BV is non-degenerate, take CV to be B C B V. So remember, so this element that we introduced, the Casimir element corresponding to non-degenerate invariant bilinear form, right? So let's take CV. Since if BV is non-degenerate, we can just take CV to be the Casimir element that we introduced before. It's central, so it acts. Okay, so we need to prove something, right? So it is. So what's clear is that it is central, and that it acts by 0 on a trivial representation. Right? It acts by 0 on trivial representation. It means that just in U of G you have like 0 degree component, right? First is G, second is G's tensor square, and so on, right? So in this element, it doesn't have 0 degree component. That's the only thing that acts by non-zero in trivial representation. Okay. So of course in our element CB, it was like this: xi. Xi, right? There's no constant term. It's already in tensor square, right? Component. In the second degree component, right? So therefore, this is also clear. So what about this one? Right. So let me compute trace of rho V CV in this case. This is a sum over I from 1 to n, right? N is dimension of my Lie algebra. Trace xi, xi. But this thing is dual to this with respect to trace form. This is B, right? So this is actually B of xi, xi, which is 1. So I have sum over ones, right, from I to n. So this is just n, just dimension of G, right? On the other hand, we know that rho V of CV is lambda times identity on V, right? Because it's central. So therefore, lambda, right? And if I take trace of this, right, on the right hand, so trace of lambda IV is what? It is actually lambda times dimension of V. So therefore, actually, lambda is dimension of G over dimension of V, and this is not 0. So if this is degenerate, so if BV is degenerate, so take the kernel, so ideal, which is the kernel of B, right? All elements in G such that B of X and Y is 0 for all Y in G. This is also we denote it as G orthogonal with respect to B. Then this I is an ideal, right? Also, restriction of Killing form to I is 0, right? So therefore, G I so therefore I is therefore I is solvable, right? By Cartan's criterion.
What is Y here?
Where here?
Yeah.
Just every element. It's kernel. You take X that is orthogonal to every element of Y, including itself, actually, right? So, right. So I is so if I equals to G, right? So I just claim that I is solvable, right? Then G is solvable. Then rho of G is solvable. But so G is semi-simple. It's already, so this is already a contradiction, right? So I don't even need this. So this is contradiction. So therefore, so this is contradiction because G is semi-simple. So therefore, I is not G. Therefore, G is I plus some other ideal G prime. And now I can take C CV to be. So now let me take my form B. So since this is a kernel, what stays in here is its restriction to here is non-degenerate because all degeneracy I kept here, right? So therefore my BV restricted to G prime is non-degenerate, right? So then take CV to be right, the Casimir element in G prime with respect to the form BV of X, Y restricted to G prime. So this guy is non-degenerate. And then again, you can check that it acts. Then it acts on V by what number? Dimension of G prime over dimension of V, which is not 0. Okay, so by the same computation as here. Okay, and then since it is also central in the inverse enveloping of G prime, right? But since all elements of G prime also commute with I, it is central in the universal enveloping of all G, because it's just direct sum. Okay, so we then the element CV is the one that we need, right? It's central. It acts by 0, of course, on trivial, and it acts by not 0 in V, right? Okay, so I consider lemma proved. So if you have any questions, just maybe let me know now or after the lecture. But now, once this lemma is proved, we're almost done proving the theorem about complete reducibility in this particular case. So again, proof of complete reducibility in the case, so I have V irreducible, it's sub-representation of W, and the quotient is trivial representation. So let me take CV. Right, and so consider rho W of CV. Okay. So since every element of V is an eigenvector of this element, right? With some eigenvalue which is not zero. This follows from lemma. Okay. So I claim that. So consider this, right? So I claim that V is a subspace is an eigenspace of rho W of CV, right? This eigensubspace in here of eigenvalue lambda, which is not zero. This is from lemma, right? By lemma, we know that we take the CV, it acts by some lambda in here, right? By lambda times identity. So each vector here is also vector in here, right? And each this vector is an eigenvector with this particular eigenvalue, which is not zero by lemma. On the other hand, so we have so actually multiplicity of this eigenvalue lambda is what? Dimension W minus 1, right? Because it's dimension V. So what is left is just one more eigenvalue, which is actually, right, but we know that CV acts trivially on C, right? But C is quotient of W by V. Therefore, this guy has to have at least some Jordan block corresponding to eigenvalue 0, right? Because if I consider quotient, then it will act by 0 in here, in quotient, right? But so the only way how it can happen is that this guy has one more eigenvalue and it is 0. In other words, so I have that, so CV acts on C by 0, this is also from Lem, right? This part. Right. So therefore, my W is V, which is eigenspace of corresponding to this eigenvalue, plus plus one-dimensional space, right? C times some vector W, right? On which CV acts by 0. Right? So when I consider quotient of W by V, right, I will get exactly this vector W. I will have exactly trivial representation. Right. But you see, each eigenspace of CV is invariant subspace because CV is central. Right. So if I have if I have right W, right, X act by some element in G on it, right, and then I claim that this vector, new vector, is also eigenvector with eigenvalue 0. Eigenvector of CV. Why? Because I act by CV on this. X and CV commute. So therefore I have X, CV, W. But then CV acting on W is 0. So this is 0. So therefore X, W is another eigenvector with eigenvalue 0. But therefore, it's just a scalar multiple of W, right? There's only one eigenvector with eigenvalue 0. All other eigenvectors have eigenvalue which is not 0. This is important, right? So therefore, XW is some scalar multiple, some C, or maybe A times W. And this A is from C. It's a complex number. So therefore, it means that this subspace is invariant subspace. So this decomposition is a decomposition of vector spaces is actually decomposition of representations. And this subspace as a representation is just trivial representation, of course. And so what we got is that W is, so we proved everything. So W is V plus C. We proved this case.